Hey students, welcome back. Today we are going to talk about buffers, all right? So buffers, what they do is they resist pH changes. So what we're going to say is that they resist pH changes, all right? And that's because they have both acids and bases present in them. So they have an acid and a base present, so that way they can resist pH changes. And so we're going to talk about that how. So here we go. So what it's going to do, it's either going to contain significant amounts of a weak acid and its conjugate base. So our key there is that we're talking about a weak acid and its conjugate base, such as like HNO2, right? HNO2 is a weak acid and its conjugate base would be NO2 minus. So anything with NO2 minus, so it could be like NaNO2 or something like that. All right, or we could have a weak base and its conjugate acid. An example here, we've seen NH3 a couple of times, so NH3 and NH4 plus. So it contains both of those. So just real quickly, our characteristics are they resist pH change. All right, so we've got it contains a lot of acid and base in it. It so the conjugate or the acid neutralizes the base part, and then the base or the conjugate base neutralizes the acid part, and that could be working vice versa. All right, but what really this comes down to is this comes down to our common ion effect. And remember, our common ion effect affected, excuse me, it shifts the equilibrium, right, away from the common ion. So basically all we have going here is we have a common ion effect. And so that's actually how you can do all the calculations just using a common ion effect. So it's not that big a deal. Or as you can see down below, we're going to talk about the Henderson-Hasselbalch equation, which is actually super simple. And we're going to get there in just a couple of seconds. All right, so this one says calculate the pH of a buffer solution that is 0.1 molar, and this is HC2H3O2, which is acetic acid, and 0.1 molar sodium acetate, all right, and our Ka is 1.8 times 10 to the negative fifth. So let's go ahead and just kind of work it like we would just any other equation, right? So here we go. We're going to write HC2H3O2, right? It's going to break apart into H pluses and C2H3O2 minuses. All right, and so what we know here is that we have a 0.1 molar of acetic acid. Ooh, that's one too many zeros. All right, we have 1.1 molar here. But let's look, just kind of take a little side trip here at NaCO3 or NaC2H3O2. So when that gets into solution, it breaks into Na pluses, C2H3O2 minuses. And so what we have there is these look very similar to these. So what we have is we have a 0.1 molar of this. And we're going to say a starting of 0, pick the wrong color there, all right, of our H plus. So then it's back to our good old-fashioned stoichiometry, if you will, or equilibrium probably is a better conversation here. We've got X, X, right? So now we're ready to plug this all in. Here's our equilibrium constant expression. We're going to have H plus times our concentration of C2H3O2 minus, and then we're going to have HC2H3O2 on bottom. Okay, now we're ready to plug it in. 1.8 times 10 to the negative fifth is equal to, we'll have, almost missed that. Did anybody see that? Okay, all right. So we're on top, we're going to have X times 0.100 plus X over 0.100 minus X. So looking at this is just the same as it has been. That minus X, that plus X are really small. So now look at this. This 0.1, that 0.1 cancels out. So X in this case is going to be equal to 1.8 times 10 to the negative fifth, which is also our hydronium ion concentration. So at this point, we can plug this in to pH equals the negative log, right? Floating away from me, all right? pH is equal to our negative log of our hydronium ion concentration. And so this little baby, whoop, whoop, right there. And our pH, we're ready to calculate. We're going to take the negative log maybe if I get everything set up correctly, negative log of 1.8 times 10 to the negative fifth. And we're going to have 4.745 because we need 3, 1, 2, 3, and there are 3 in our concentration. Boop, boop, boop. Ka and Kb we don't actually use for our significant figures, all right, because they're considered kind of exact numbers. All right, so how's that feel? Pretty good, right? We've done calculations like that before, so it shouldn't be super stressful. Now let's move on just a little bit and try what is called the Henderson-Hasselbalch equation, and this is just supposed to make that calculation very easy. You don't have to use the Henderson-Hasselbalch equation, but you're welcome to if you want to. All right, so if we check here, here's our Henderson-Hasselbalch. pH equals the pKa, we'll get to that in just a second, plus the log of A minus the concentration of A minus over HA. So let's real quickly talk about pKa. pKa is very simple. We're just going to take the negative log of our Ka. All right, that should be simple. And then log of the A concentration, A minus concentration, and the HA concentration. And this is just what's given to you in problem. All right, you don't have to do equilibrium. This is just usually given to you in problem. All right, so this makes it very, very simple. So let's see if we can't solve that problem for this one, our benzoic acid. So it says calculate the pH of a buffer solution that is 0.050 molar in benzoic acid and 0.150 molar in sodium benzoate, and our Ka is there. So we're looking for our pH. All right, our Ka is that, so we're going to take the negative log of that 6.5 times 10 to the negative fifth is equal, no, excuse me, Griffith, come on. All right, so plus, how about that? The log of our A minus, which is going to be our sodium benzoate concentration, which is 0.150. All right, over our concentration of 0.050. So remember with logs, we have to do those first. So let's go ahead and knock those babies out. Let me pick up the right calculator. All right, so we've got negative log of 6.5 times 10 to the negative fifth. That's going to give us right here 4.187. All right. And then there, we're going to take 0.15 divided by 0.05, right? And then take the log of that. All right, and we get 0.477. So we add those two together, and we get 4. What do we need? 2 there? 4.66. Our pH is going to be 4.66 there. So that actually makes that common ion pretty simple. All right. So what we have to do here is we have to, if we calculate pH changes, a lot of times we're going to be asked to calculate pH changes. So the first thing that we have to do is we have to do the Stoich calc, and then we have to do the equilibrium calculation. So that's where we would use our Henderson-Hasselbalch, but sometimes we have to figure out how much is used up or whatever. So let's take a look at this next example. All right, we still have acetic acid. Make this a little bigger, hopefully. All right, so we have a 1 liter buffer solution. It contains 0.1 mole of HC2H3O2 or acetic acid and 0.1 mole of sodium acetate. The value for Ka as acetic acid is 1.8 times 10 to the negative fifth. Because the initial amounts are equal, the pH of the buffer is equal to pKa, right? Which makes sense, 4.74. We calculated that above. Calculate the new pH after adding 0.01 mole of solid NaOH to the buffer. For comparison, we're supposed to calculate just NaOH to water. So let's start with that part right there. So we're going to talk about adding 0.010 moles of solid NaOH to 1 liter of pure water. So that's going to be really simple. We take why am I in the highlighter? All right, we've got POH is equal to the negative log of our hydroxide ion concentration because we have a strong, we're looking on this one right here. All right, and we have a strong base, right? So to get to the molarity, right, we're going to take the negative log of 0.010 because 0.010 divided by 1 is 0.010. So this would be our POH if we just threw NaOH into water. And we probably should have done that one in our head, right? POH is 2, pH is 12. That feels pretty aggressive. We would not want to put that on our skin or anything like that. So let's see what a buffer can do for us and kind of take us from there. Okay, so now we have to look at our reaction. We have acetic acid reacting with NaOH. And this is just a good old one direction reaction. We're going to get water and sodium acetate. Okay, both of these are products in our equilibrium constant expression, right down here. Beep. We'll write that out so we can kind of see the commonalities there. Right, these are gonna match up, this and that. All right, so let's see what we got here. So initially we started with, where are we at? 0.100 moles. All right, and over here we had 0.100 moles. And now we also have 0.010 moles, right? So according to stoichiometry, we're going to use up all of this, the 0.010, right? Which means we're going to add 0.010 on each side, which gives us 0.110 here on this side. Water we don't care about, right? And then we're going to only subtract, I don't know why I was putting an X there, 0.010, right? Which is going to give us 0.090. So there's our moles of acetic acid and our moles of sodium acetate, which we can now convert to equilibrium, right? Or plug them into our Henderson-Hasselbalch, but let's find those. So to find each of those, we have it in 1 liter, right? Are they both in 1 liter? Yep, we're doing 1 liter here. So we divide by 1 on each of them. That would give us our molarities, right? So our molarity here is 0.090, and our molarity here is 0.110. Okay, now we're ready to plug that into our Henderson-Hasselbalch. pH equals pKa plus the log of the A minus over the HA. And let's plug that in, right? Well, we know the pKa is already up there, that 4.74, plus the log of our A minus, which is that 0.110, over our HA, which is 0.090. Blow this up a little bit, maybe we can see it. All right, so let's see what we got. We've got 0.110 divided by 0.09. Okay, now we take the log of that. I'm hitting all sorts of buttons wrong. All right, so that gives us, that is terrible. Let's try that again all together. All right, that is 0.087. All right, and plus 4.74. And yes, Josu is drinking water in the back like she hasn't had water in a while. All right, so we're going to get 4.83. I was just trying to look for sig fig. So our pH is 4.83 versus that 12. So obviously this does a really good job. The same amount of base, right? One's just in water and one's in a buffer solution. So the pH went from 4.74 to 4.83. That is so good compared to jumping 12 pH units, all right, which is power of 10. So we're like talking about 12-fold. Okay, so let's see one more time. The only thing here is we could have a base, which it works the same way. So instead of pH, right, here's our Henderson-Hasselbalch originally, pH equals pKa plus the log of the A minus, concentration of A minus over the concentration of HA, right? We're going to have POH equals the pKb plus the log, can anybody guess? OH minus, yep, over our concentration of just B, right? So it's very, very simple, all right? Is that a B? That should be a B, but it looks kind of like an A, so let's try that again. All right, and then from POH we can get to pH, right? So let's go ahead and plug it in. We know that that is 4.75 plus our log of 0.2 divided by 0.5, and that'll give it to us. All right, so this is going to be like a negative 0.3979, and we're going to add 4.75 to it. So we should get 4.35. All right, so our pH is 4.35. pOH is 4.35. So our pH is 14 minus that 4.35. And we should get a pH of 9.65. All right, that is our Henderson-Hasselbalch and our work with buffers. All right, see you next time.